So now we're going to hear from the man who more or less started it all. Right.
All right, can you hear me?
Yes.
Yep. All right, well, thank you, sort of, Randy and David, for inviting me. So I'm going to, this is the title that I think is convenient when I don't know what I'm going to say. It's also the basis of understanding decision making, which involves not just what we're deciding, but how long it takes for us to do so. In other words, optional stopping. Now, before I understood that this was going to be a debate, I looked at the list of questions, and I thought, boy, it would be fun to talk about a lot of these topics. Oops. Let me set this up. And so what I wanted to talk about, some new results, rate coding, single neurons populations, other forms of obfuscation, high-dimensional codes, in other words, representation, provisional affordances, which maybe I'll get to tell you about, and the difference between processing and interrogating as a metaphor for what knowledge is in the brain. And maybe we'll get to it, a little bit about time, and a little bit about neural noise. But neural noise turns out to be something I think I've gotten dragged into now. So I'm going to address, drawn into this cacophony of another kind. Okay, so I want to just share with you why I study decision making, and that is, I have to tell you, some of you probably don't know this, but I'm a neurologist and I care about diseases that affect higher brain function, and I feel we are stymied right now by not understanding the basics of what it is about a normal brain that makes us not confused. So evolution, the way I see things, is that the emergence of cognitive capacities was accompanied by an expansion of the cortical mantle, monkey, mouse, humans, and most of this expansion was devoted to association areas, and many neurons in those areas have a long time scale of their firing, of persistence, that's usually associated with working memory and planning. And I think that this persistent activity holds the key to cognition because it confers a kind of freedom from the immediate demands of sensation and action. Evolution, the rudiments of cognition, were in that freedom. And we'll talk about that. And we study persistent activity in a convenient place to study it, but it's only one of many places, and I want to emphasize that. And that's this area called the lateral intraparietal area. This is the parietal sulcus here. That amount of cortex is about a mouse's brain. And this is the slice through the brain at that level. And the lateral intraparietal area, LIP, especially the ventral division, was defined by Richard Anderson based on its projections, part of Broden's Area 7, its projections to the frontal eye field and the superior colliculus. And that makes it an interesting area to study the convergence of its inputs, visual information, most of it indirect, but ultimately connected to extrastriate cortex, and its outputs to control eye movements, which is what we train animals to report with. And so they have a kind of activity called spatially persistent persistent activity. If you ask a monkey to make an eye movement to the briefly flashed target here, this is what a neuron sounds like. All those spikes, what I would call persistent activity, they represent the monkey's plan to move his eyes from here to here eventually, or you could say attention to here, or the salience of this place in space. These are just words for this phenomenon. Those are the spikes you heard on the speaker. And notice, this is the steps. Low firing rates, high firing rates. So the defining feature of area LIP is that it can step from one firing rate to another firing rate. That's why we study these neurons, because we think they confer this freedom from immediacy, the ability to use information from the world in a time frame not dictated by the changes in the world or the need to control body musculature in real time. And the evidence for spatial selectivity is that target was flashed over here. Here's those spikes, and you see no elevated persistent activity from the time of that flash, and the monkey's eye move over here. So what we can do is, not all neurons in the association cortex have spatially selected persistent activity, but the persistence is the ubiquitous feature and the important one. But spatially selective persistent activity allows us to study these neurons by contriving tasks to make a particular place in the visual field an answer spot where I thought something was moving to the right, or I thought that the confluence of information from a set of symbols means that's where I should go, and not that. So this is a neuron that we know ahead of time, A, could step or not step, and we know that it is probably going to tell us something about whether the monkey plans this eye movement or that eye movement. And so that's what we do. We study that in the context of decision making. Now, I want to just frame the debate, as it's called. I don't really see it as a debate. I see it as a tremendous amount of knowledge about a topic and a few faulty papers. So so I'm going to frame the issue. You're going to see that I'm going to end up agreeing a lot with the previous two speakers, which is not something I actually expected, but I do. So let me try to frame this carefully, and we'll see if we all agree. My presbyoptics are acting up, so I need to put on my glasses. Let's see, in the language of this, what are we trying to explain here? Let's be really precise about it. So it's that the average firing rates from area LIP, from these neurons, that are attained during the formation of a decision, which is based on an accumulation of roughly independent, identically distributed samples of noisy evidence, appear ramp-like. Okay? Now, there's little footnotes associated with these, each one of these little parts of the claim. But the point of agreement is that we're going to look at a task in which evidence is being accumulated over time and ultimately gave rise to some kind of firing rate that looks on the average ramp-like. Okay? So then the hypothesis that, say, we put forward over the years is that those averages comprise single trials whose latent rates, and I'm using it in the Jonathan sense, represent a discrete diffusion process. Okay? So, and the alternative hypothesis, of course, there are many alternatives, but the main one is that the averages comprise single trials whose latent rates represent stepping from a neutral to either a high or a low firing rate state. Okay, so that's the way Jonathan framed the question. I thought of that actually in the very first papers we were working on in Bill Newsom's lab. Something that was cut out of our J-Neurophysiological paper was a whole Comenges and Seal have the optimal way of finding a step. I thought there was an appealing idea that sort of analogous to the size recruitment principle in the motor system, that maybe a diversity of stepping among single neurons in the association cortex might, in the population, give rise to accumulation. We found no evidence for that, and the reviewer made us keep it out of the paper. It involved all kinds of things like PICs and stuff like that before they were popular. So I would say that a critical distinction between these two alternatives is that latent rates during evidence accumulation represent several, as opposed to the alternative being, at most, one non-neutral state. Okay? That to me is the key. Okay? That is a way of connecting an abstract idea to one that I think has biological significance, really a principle. And that is that the nature of persistent activity, whether that's what it's addressing, it's whether single neuron firing rates represent quantity, intensity, degree of belief, degree of something else, numerosity, you name it. Okay? So that's a question. The idea is that computation at long time scales might involve the substrate of working memory, which we could think of as a step or not, but the hypothesis is that actually these neurons take on intermediate values. Okay? And I think that's important. I really think in some ways it's a battle for the soul of the brain. Okay, so, right, let me just fill in the little details here, and you can like, phase out if you want to. Which is that, first of all, we're not talking about all, it's really hard to see from here. We're not talking about all LIP neurons, and we're not talking about only LIP. You'll see an example of that at some point during the talk. So there's nothing special about LIP. We just contrive tests that we can study. We hope it's a general principle in this particular area. We would be sick to our stomachs if we discovered we found a mechanism that only had to do with figuring out which way random dots are going. So number two, evidence. That's IID. I'm going to qualify IID. The evidence samples are not truly independent and identically distributed at fine time scale. they are, what I mean by fine time scales, say anything less than about 40 milliseconds, which is about the the time constant, the decay time of a firing rate of a sensory neuron in the visual cortex. Okay, that might be the outer edges of it, and also because the stimulus itself, as Era points out, has some autocorrelation. We're talking about motion. There's a delta t in the definition of motion, and of course the sensory system has to integrate it and then leak it away because it's keeping up with a changing world. Okay. Now I want to one quickest. Okay, let me do a couple more. Evidence samples can increment or decrement the accumulation. Okay, that's important. In other words, we're talking about the accumulation of a difference variable, something, a random variable whose support includes negative and positive numbers, okay? And so that means that we're talking about a process that looks something like diffusion, except for this qualification with respect to IID. And because of optional stopping, the average is ramp-like only at the beginning of the accumulation. The departure from ramping is a consequence of the state of the stop variable and the attrition from the averages of trials that have already stopped. Okay, so all of these things, there's no disagreement here, I don't think. The only disagreement I think might be with Konrad, because I would never ever think about the individual trials as ramps. Okay, I might play a game to try and get it, and I think that's what you were after. But no single trial should be thought of as a ramp. It's either, I think the interesting thing is whether the average that looks like a ramp was formed by something else, these other two considerations. Now, I want to point out that 2 and 3 are reconciled, and someone raised the question of a continuum between diffusion and stepping, and essentially it's just diffusion. It's just accumulation over a very brief pulse. It looks like a step. Okay, so those are but anyway, 2 and 3 are reconciled by discrete diffusion or integration of a low-pass filtered white noise, like a Ornstein-Uhlenbeck process that is then integrated. Okay, so anyway, I'm going to use the term diffusion and evidence accumulation, noisy evidence accumulation. The critical thing is that it's a form of sequential sampling with optional stopping. And that way, we're going to reconcile choice and how long it takes to make it. So the outline of the rest of the talk is we're not going to get the part that's time permitting. But we'll talk about behavioral evidence for evidence accumulation, and then we'll talk about the neurophysiological evidence for diffusion-like things and stepping. Okay, and then we'll see. If there's time, I'd love to talk about neural coding and firing rate variability and affordances and stuff. Okay, so this has been, Konrad did a beautiful job introducing this, so I can fly. Monkey decides between the net direction of a random out motion, and tells us when he's ready that he thought the motion was to the right or to the left. And to summarize a lot of work, we basically think we understand a lot about the process. Noisy information from the stimulus gets transduced by cells in the retina, LGN, ultimately the direction selective neurons in the area V1 and the extrastriate area MT. And that's all sensory, momentary evidence because it's keeping up with a changing world. Little fluctuations in here, and we do keep our seeds, we can reconstruct our dots. Those things are probably giving rise to noisy fluctuations in the sensory, momentary evidence, the sensory representation, which I'm representing here as a Gaussian on its side, is just to say you're getting random numbers from these momentary evidence that represent the difference right minus left, okay? For a right versus left discrimination. I'm not going to present the evidence for that claim. The idea is that neurons with these longer time constants can have the capacity to accumulate that momentary evidence, and this might be the path of such an accumulation until it stops at this upper bound. In that case, that upper bound means that's the stopping criterion to say I've had enough information, the answer is rightward. Okay? In this simplified depiction, the lower bound would be stopped for left, and you can see right away that this basic formulation reconciles the choice that's made and the time that's taken to make it. And if we put these bounds, just to give you a feel for it, if we put the bounds closer to the starting point, then this trial would have ended with a left choice at the savings of time. So you get the idea that it mediates the speed-accuracy trade-off, and it does in some ways. All these statements require qualification. And in data from monkey, if we plot reaction time, which is the elapsed time between onset of the motion and the beginning of the eye movement, And we plot that as a function of motion strength. It's a funny axis. The most difficult conditions are at 0% coherent motion. The weakest motion is all really noise. Monkey doesn't know that, though. So, he's just trying to make his best guess based on the little fluctuations in the stimulus. And it takes him the longest around there. And the strongest rightward motion on this end of the axis, the strongest leftward motion indicated by the negative sign on the left side of the axis. This is the example I just showed you. And then it's taking on the order of 400 milliseconds, okay? And what you can do is fit these data with the equation that describes the decision time plus a non-decision time that's the sensory and motor components. A bunch of components we don't understand. It's a larger number than you might expect from just thinking about latency. So this B I've already introduced to you. That's the bound heights. It basically again, mediates the trade-off between speed and accuracy. And there's only one other term in this, which is a number, k, just a constant, that multiplies the motion strength that I'm plotting on the axis here. And that just converts these arbitrary units of motion strength into signal to noise. Okay? And there's this non-decision time, which means it is possible slower, but you see it just kind of lifts a part of the curve. You can be slower for left choices than right choices. You aren't in this data set, but you could be. And so think of that as, at least in the mean, an offset. If you think about distributions, you have to think of it as a convolution. Okay, so now the interesting thing about this, and what got me all excited about this, was that since the single process reconciles choice and reaction time, it turns out the equation for essentially whether you're going to stop in this bound versus this bound is a logistic function. It turns out of those same two parameters. Now we use those two parameters to explain the reaction time. So we're left really predicting what the choices should be. We're saying at this strength you should always choose right, at this strength you should always choose left, and this is the rate in between, and this is where the data lie, which is pretty close. Now for a long time, I thought that that basically sealed the deal. It's accumulation to bound because it's very hard. How could you imagine being able to predict one set of observations with another under any other set of ideas? And then a very talented graduate student, who I don't want to get too big a head, I would say nicer things about you, Gabe, if you weren't here. I mean, Gabe. He likes to be called Gabe, by the way. He convinced me that's not exactly true. We'll come to that in a second. Now, I should say we did not invent this model. It was really proposed during World War II by Abraham Wald, who was doing munitions control, quality control work. Secretly. It was all classified until, luckily for us, the late 40s, till after the war. It was also, let's say luckily, because he died in 1950 in a plane crash with his wife giving lectures in India. And then it was also co-discovered by Alan Turing in his code-breaking work, and that wasn't even, it was kind of back-of-the-envelope stuff, but reported after Turing had already taken his life, when the Bletchley Park work was declassified in the late 70s, it was and the famous Bayesian I.J. Good, who went by Jack Good, wrote all about Turing's contributions to probability and statistics during the war. And then a lot of people brought this into psychology, mathematical psychology, and perception. And I'm just listing a few of the main players here. But for students, if you already consider yourself an expert in signal detection theory, and if you're a psychologist, you have to be, then you should also read Stephen Link. He's not read enough in our community, and I think he had some great things to say. Now, a few other qualifiers I want to point out. First of all, the bound is not, this is a point I want to just kind of correct Konrad, I think it was just being quick, is the bound is actually not a stopping point on belief. It's not a probability of being correct, it's not the posterior probability of making the right choice. It would be if there was only one motion strength. But because there's a lot of motion strengths, you don't really know, the assumption is, that as you're deciding about the direction of motion, you're learning effectively as time goes by, perhaps, whether it was likely that you got an easy or a difficult trial. But the bound represents a different amount of belief. And it turns out that the optimal solution for deciding between two hypotheses is not a flat bound. The normative solution is a collapsing bound, because as time goes on, it's increasingly likely that the world has dealt you a crappy source of information. It's like turning on Fox News. Okay, and I'm sorry to even call that news, but in any case, the optimal solution, and this is derived by Ruben Moreno-Bote and Jan Drugovic, who at that time were postdocs with Alex Pouget, very beautiful paper there. And so that's, you can find out what these bounds are by solving dynamic programming. Okay, fine. The other thing to say is that in the brain, there's not a race, it's not an accumulation between an upper and lower bound. There's a mechanism, as you can imagine, that cares about the right answer, and there's another set of neurons that care about the left answer, okay? So it's really a race between two diffusion processes. I'll use the word diffusion just to emphasize that it's still an accumulation of positive and negative little steps, okay? But of course, this is the accumulation of right minus left, and this is the accumulation of left minus right. So they're going to be, because of the stimulus, highly anti-correlated. On the other hand, they're not perfectly anti-correlated, and that leads to something I'll point out to you when I show you the physiology. Okay. All right. Now, of course, if we want to implement, nice thing about a race is that first of all, it extends to more than two choices. You're going to race among n possibilities. So that's kind of nice. And the other thing is that it gives you different ways of implementing changes in the bound height or even the bound shape. Instead of doing this, we could, do this to both bounds, or equivalently, we could leave flat bounds, flat thresholds for stopping, and just add some time-dependent function, which we call the urgency function, U of t, to both accumulators. And we see evidence for that in our recordings as well. In other words, a time-dependent but evidence-independent signal is added to all accumulators. Okay, so now, I forgot to make a call. Do I stop making a call? I won't. Okay, so let's see. I want to emphasize this point, that during formation of the decision, this business, that we're all going to kind of agree that we want to make sure when we evaluate evidence, say for stepping and ramping, that we're dealing with, I shouldn't have said ramping, I'm going to avoid that, stepping or diffusion accounts of what on average are ramps, okay? Let's be really careful about that. We want to be clear that we've satisfied those conditions in our data sets. And I'm going to argue that very few data sets do. So this is Gabe, as I mentioned a moment ago, and a very talented postdoc. You've already heard his name brought up a couple times, Ariel Zilberberg, who's also here, both of you guys. So Gabe's been sort of spearheading this project of alternatives to integration. So there's integration, there's the momentary evidence, here's this accumulant, just a sample diffusion path, diffusion with drift, and integration, and its stopping time. Okay. Now, here's an interesting alternative. We call it, this is a sequential sampling without memory. We call it the extrema model. Okay. And the idea is that you get a sample, say, and if it's less than your threshold, you forget about it. Okay. Remember this. You get a bunch more samples, so finally you get this one sample, one furthest to the right, and okay, so now you answer, you've exceeded the threshold, and you say, stop at that time, I answer left. Okay? So we call that the extrema model, and it's easy to analyze this model, exponential distribution, principle of decision times, and so forth, of course, convolved with non-decision time, whatever that really is. And so that's one model. Okay, so let's look at the other ones really quickly. There's integration, there's the extrema model, and there's one other one I want to throw out there because I think it's actually really prevalent in the literature, but people don't know it, and we call that the snapshot model. It doesn't have any prescription for reaction time, so you can make up whatever you want to. It sort of separates out reaction time from choice. But the choice is that sometime while your stimulus is on, take a look. For some reason, I don't know, maybe some interesting looking sounding click on some place, or maybe some light that just captured, or just because time was running out. It doesn't matter. Whatever it is, for some reason, take a look and then do signal detection theory. Compare your sample to a criterion, and if it's above your criterion, say right. If it's below it, say left. Okay? And so we call that the snapshot model, and we think it's very hard, I think anyway, it's very hard to exclude this model from any, I'm sorry, I'm getting ahead of myself. Let me just say that if you have a data set that is this choice model, these are choices, they were produced by integration, extrema, and the snapshot model. And if we do what's called psychophysical reverse correlation, you look for the aspect of your stimulus, the little extra motion to the right or to the left, whatever it's going to be, and you say when did I tend to see that when the animal answered in favor of that, or the human? Okay, we call that a kernel, and we say, wow, it's flat. It must be that the animal must be using all the information. Well, across trials, he's using any particular time, but within a trial, there's nothing to say that he's actually the animal is actually accumulating anything. Okay, all three of these models can give you these kinds of kernels, and all kinds of shapes of kernels if you free enough the parameter or two. Okay, and so I'll submit to you that most of the experiments in the literature, I'm not picking on Jonathan and his collaborators, but I will in a second, but I don't really mean to single them out, is that I think this is true. I mean, the entire rodent literature, I think, is that has claimed any evidence for diffusion, I read with great suspicion. Okay, so it's a little ironic because I'm kind of doing an averaging artifact kind of argument. Okay, so now, so let's see, I want to say this. Can we save the day here? What does it take, you might say, to know just from the behavior, without relying on the physiology, to know from the behavior that you're dealing with a situation where there's accumulation? That is one of the conditions that you want to ask the question. Well, what are those latent breaks that gave rise to those things that look like ramps? Okay, well, it's kind of hopeless to do that with just reaction time too. I won't say it's kind of hopeless. It might seem that you should be able to do this, fit this and predict this, but you can do that with the extrema model if you're careful with the parameters. Let's see, what else could you do? You could, that's not good enough, but it's getting close if you have reaction time. You could put a subtle background pulse in the stimulus early on and see whether it affects choices in reaction time hundreds and hundreds of milliseconds later. If it does that, that kind of rules out the extreme model. Okay, what else could you do? Did I miss something? I feel like I missed something. Maybe not. Okay. Well, another thing you could do is you could do an experiment in which you control the durations, but you control them to be super short, like 100 milliseconds or less, to very long. Okay. When you do that, you don't want the animal to anticipate time, so it's best to do it with an exponential distribution of durations. But when you do that, then what you can do is you can fit your diffusion or your extrema model, and with that you can make a prediction of the improvement in sensitivity to motion. So these are like thresholds, you could say, of whole psychometric functions plotted as a function of stimulus duration. Okay, and there's a way that the integration model should work. We're talking about integration up to a bound, because even when you control the viewing duration, it turns out that the brain times out at a certain point. Okay, so as Jonathan pointed out, there is a sense in which that you can, even if you're not measuring reaction time, have a bound that terminates the accumulation of evidence. Anyway, what you do is it turns out in our data, this is data from 2 monkeys. This is one of the 2 monkeys. The other monkey is just as good, actually looks even better. Is that if you effectively predict the rate of improvement in a variable duration experiment, and it's a complete miss with the extreme of it. Okay, so if you can do both of those, that's a lot of work, right? And most of us are not going to do that. But if you do, it is possible to make a case that your animal really is integrating over long amounts of time. Okay. Okay, so then, what was I going to say about this? Oh yeah, another thing is that one of the ways that extrema model does as well as it does on fitting reaction times and choice is by playing around with the non-decision time. Because remember, I mean, the decision time should be exponential, so it's a matter of what you do with the non-decision time. So that gives you a handle to evaluate it. And what you could do is you could say, well, you have a new prediction, which is if you gave a really strong motion stimulus, it should go down to the non-decision time. And it turns out that you predict these reaction times, and at least in one human observer, we can predict that amount of time. So we think that it is possible with reaction time. There's a few other tricks I could have shown you. That if you do choice reaction time and the reaction times are long, then you can tell the difference between models that integrate and mechanisms that involve integration and mechanisms that don't, whether they're just arbitrary times, or in this case, the more difficult competitor for the diffusion model is the extrema. Okay, but one important point is that I think without measuring reaction time, it's almost impossible to conclude that your animal is integrating over the kind of long time scales that are presupposed when we argue about whether or not the underlying latent dynamics are steps or ramps. Because once again, as someone pointed out, along the continuum between steps and ramps, it's just a short integration time. You know, if you get a little pulse of information and you integrate it, it will look exactly like a step. Okay, so a little bit of smooth step, you could never tell from data. You remember data on single process spikes and gaps between them. Okay, so, all right, so this kind of behavioral prerequisite for the for this debate is that if the snapshot and extrema mechanisms are not excluded, there's no point in comparing the models of evidence accumulation. Snapshot and extrema mechanisms would result in asynchronous stepping or fixed or variable but long duration experiments. Okay, so what I meant to say that there, I didn't parse my own sentence right, is that you would see something like asynchronous stepping if these alternatives were at play, simply because there's only a single element, there's only a single sample that led to the choice. Extrema mechanisms would produce approximately synchronous stepping. I say approximately just because of the variability in the non-decision time. And unless integration occurs for over 100 milliseconds, I would say a lot more than 100 milliseconds, diffusion and stepping are indistinguishable. And I think these concerns apply to the main data set that was analyzed in the famous paper from, the bombshell paper from Jonathan and his group. And so, the evidence for that, I think I won't spend a lot of time on it, it's not really worth it, but you can look in the technical comment that we wrote, and Jonathan dismissed rather readily, that looking at the performance of these animals. The animals that were studied never saw anything less than a half a second. And the idea that these animals were integrating for more than my estimate is 80 milliseconds. But if you're generous and you say that lapses, that the errors are all owed to lapses, then you can get up to something like almost 200. But in any case, we thought there was very little evidence for integration in that data set. So for me, it was a non-starter to even think about it. But I was forced to, thanks to the Shadlen thread that Konrad referred to. This is the new problem with Twitter, in my view. So now let's go to the neurophysiological evidence for diffusion and its alternatives. One only alternative I'm considering right now. Okay, so you saw a version of this graph before. I've simplified it by just showing you 3 motion strengths. These are the trials that are going to end in a choice for the target and the response field. These are the ones that are going to go to the other one. Okay, I'm just going to fly through this because you've seen it all. These responses seem to come together before the saccade. Now notice they don't come together when the animal chooses the opposite direction, indicating that there is really no lower bound. What there is just an optionally stopped process due to the other winning process. That is not actually a threshold. Okay, so adding a new threshold to the lower bound is a new problem. You guys have to beat that up, I think, Jonathan. But in any case, these trials are also optionally stopped, but not by the process you're studying. So they retain a lot of stimulus-dependent variability where this loses it. You see the loss of it up here much easier if you include all the trials and then group by quantiles of reaction time, fastest, slowest, and you see they come together about 80 milliseconds before the saccade. I've dropped that arrow down to show you that. I'm going to call that roughly 100 milliseconds. And also you notice this latency here before the information that in the visual stimulus, which is turned on at time 0, before it affects the neural responses, that's on the order of 200 milliseconds. And basically our non-decision time is about on the order of 300 milliseconds. Okay. So, and by humans, when we do hand movements, it's about 350 milliseconds. That's collaborative work with Daniel Walpert. And it's, these are consistent numbers in the mean, but they are also probably variable. Okay. So one other point I want to make is that if you look at the responses here, this is a general point for people who are probably going to speak tomorrow, is that you can, as a statistician, decode the answer the monkey is going to give you on the trials. You notice all these solid curves are above all these dashed curves. These are the right choices, say, these are the left choices. This is average data. Okay, but you would say I've had a population of data that I could decode what the answer is. In fact, the monkey's effectively in choice mode here. But actually, just because you can decode it doesn't mean the monkey could. That's why we do reaction time experiments. The monkey tells us often that he wasn't ready to give an answer till a second later. Okay, so your decode, the experimenter or the statistician's ability to decode may have very little bearing on what the brain does. I think that's a really important one of my take-home messages for you, even though it didn't make it into my summary slide. Okay, so it's all the rage now, decode. Now I want to make another point. I've been showing you these averages, but those are not the averages we're talking about. Those averages were conditioned on the choice. So when we think about the decision variable, which is all the stuff that we're all interested in understanding, you know, what is going on at a single trial level, stuff that I think Jonathan has worked on so elegantly, even if ultimately concluding incorrectly, these are the averages that more depict the decision variable, but they have their own problem. So they better characterize the decision variable, DB, in the sense that that's the accumulating evidence that could lead to either choice. Okay. Now, obviously, that means that as you go out in time, a lot of these responses that you see in the average are just admixtures of trials that will go to the upper and the lower bound. Okay. So, I mean lower bound, mean optionally stopped by another process, but I'm going to call it lower bound. Okay. So, and so these are kind of only ramp-like for a little while before that attrition. That was one of my footnotes in qualifying notes in that first slide. So I just cut out the first 150 milliseconds, and if we just sort of stretch it out, it begins to look kind of ramp-like. Okay, and so my view is that you really want to think about the period of time where if you want to try and think about ramps, if you want to as the average, then and model that. Well, then you only have a small amount of time to do it. But you know, the fact is that you can model the whole thing, just we just have to recognize we're not really talking about ramps here. I think it's confused people. I can confuse Konrad. Okay, so so now let's I'll just give you an example in a variable duration task when you really do use very short to very long durations. We see these kinds of things in spades. So this is this is LIP. This is from a different monkey, same monkey recording reaching, and we're recording from MIP. We see the same thing. So nothing really unique to LIP. These things are going on oftentimes simultaneously in the brain. There's MIP and LIP on trials with the monkeys reaching. A little muted over here. Okay. Okay. That's just all the qualifiers on ramping, and that's just a prerequisite. We need to have ramping in the averages, and we needed to have something where we believed that we had a chance of seeing evidence of accumulation going on. Okay. Now let's talk about the thing that's about rate dynamics on single trials. Now this is very challenging, and because the latent rates from diffusion are unidentifiable. And that was the argument that Jonathan and Konrad were having. I have to side with Jonathan, having worked hard to try to find ways to identify those latent rates, and failed. And so I'll tell you what we did is instead of using that, and Jonathan mentioned it, we just resorted to second-order statistics to look for signs of diffusion. And second-order statistics meaning the evolution of the variance, which, you know, it's something that represents the sum of independent numbers, which, by the way I'm going to get away with independence is that I'll say independence sort of in discrete times, so that I can get away from the autocorrelation times. So it's as if I go long enough. It's as if I got a new independent sample. Okay, that's important. That's why in order to for us anyway, you have to have long reaction times, or you have very few independent samples. Okay, and then you can get away with things like linear ballistic accumulators and later models of Roger Carpenter and so forth, because then effectively all you really have is a change in slope because you have one parameter. Okay, so anyway, so the variance, that's intuitive to you, I'm sure, that the variance should increase linearly with time, and that's a signature of the diffusion process. It's not a unique identifier of it. The other one has to do with the auto covariance. And so what we did was we just we married the theories of doubly stochastic point processes, the latent rate being the rate, and that's already stochastic. Okay, so it's a sample from diffusion. You could call it a Gaussian process of a certain kind, and then the doubly stochastic is that they're spiking. We only get to observe the spiking. Okay, so but we married that with the law of total variance, and from that we could extract a quantity called the variance of the conditional expectation. Please read the paper. I think it's a cool way of thinking about things, Okay, so that's one thing you can do. And then the other thing you can do, oh, here's another paper that people don't read, and I think this guy, Mark Narod, doesn't get enough credit for this beautiful paper he published in Neuroscience Methods about what's called a generalized renewal, which we depended on. There are a lot of weaknesses of this approach. It was the best we could do. But we think we can take spike train and we can extract from it with this one little nasty parameter, which is effectively a Fano factor, but not one you could ever measure. It's like a moment. It's like a mean. It's owned by. It's a property of a random variable. Okay. In this case, it's stochastic point process. But anyway, there's something called the generalized renewal, and we relied on that idea. So then you can apply that also to covariance. Yeah. So there's a law of total covariance as well, and that's kind of neat because the idea is if I told you the rate at this time, the underlying rate, and I told you the rate at another time, then conditional on that, you have two independent point processes, by construction. That's what we would say. Okay, the point process is just local to the rate at that time. But that means that it's very easy to actually estimate the conditional covariance, the conditional expectation of covariance. Anyway, so it turns out that the neat thing is that if you normalize the covariance matrix of the latent rates, it has no degrees of freedom. In other words, if you make it a correlation matrix, then if let's say these are 6 actually, 60 millisecond bins, let's say. Okay, so I got a 6 by 6, which means if I thought about it, a correlation matrix will have 15 unique R values, right? 36, take off the main diagonal, divide by 2. And these are what they are. They're all square root of I over j. Okay, that's it. So we can use that. That's a really neat and a much more discerning signature of diffusion. And when we applied it to this data set, for example, we get beautiful conformance with theory. We have 1 degree of freedom, this phi value, but we can explain it in all the conditions except for the one that gave us weak responses. Now, I used to think this was really interesting, but I'm pretty convinced, thanks to a really critical reviewer, that it's not because this is not diffusion, but probably, at least we can't rule out that it's just a weak response. Okay, so that's one way, and I'm not going to say it's the best way. I would really love to see the techniques that Jonathan has been championing work. I know they work, but I mean, work in the proper model. I'll come to that in a moment. Okay, so then one other thing we can do that was left out of the big debate that we witnessed before the coffee is you can do this thing that we experimentalists call experimenting. So we can design experiments to examine the critical properties. So, for example, I care about whether or not, as I said, it's the soul of the brain question, whether or not persistent activity, in variety of structures, but let's say in LIP, represent intermediate quantities. So here's a simple experiment. Have the monkey anticipate the time. He has to see a spot and make an eye movement to it as soon as this thing dims just ever so slightly. And provided he doesn't jump the gun, the faster he goes, the more reward he gets. And that's that. Except that what we do is we vary this time, and we vary it using a bimodal distribution. We do other ones too, but this tests a particular hypothesis that maybe these neurons represent the anticipation, which technically is called a hazard rate. Anyway, it's obvious what this is telling you, right? That these could happen at half a second, never at 1 second, but oftentimes at 2 seconds. I'm going to show you a movie of a single trial of a neuron, and it's this neuron. I'm going to pick a trial that was really where the monkey had to wait a long time, but he'd been exposed to this schedule of a bimodal distribution of waiting times, and you should get ready to hear an anticipation function that anticipates that first mode, but then dies off and then goes like crazy to anticipate that, as enough time goes, it's very likely the ghost signal is about to come, right? Here we go. Right. That's so you can hear it. It's a lot of people don't hear it. Okay, anyway, that's single trial. In the lab, we hear single trials doing things like stepping up and stepping down and doing a lot of things during single trials. So to us, it's just a no-brainer that these neurons, at least at the biological level, are not built to step into a high or low rate. To me, that's what matters about the debate. It's really a how the brain works question. Is persistent activity kind of like high-low state, or is persistent activity a substrate of computation? There's an example. It's rare that you do get to hear a single trial from a random neuron in the parietal cortex showing you what the computation is. It's what we call subjective hazard rate because of scalar variability of time that Randy can tell you all about. Okay, so okay, here's another one. I want to give you a few more examples before. How am I doing time-wise, by the way?
I gotta look through my notes.
Right. Okay. Yeah, we're definitely not going to get to all the cool stuff. Okay. So okay. Here's another example: probabilistic categorization. A monkey sees a series of shapes, has to decide based on the weights we've assigned these shapes that he has learned over many thousands of trials that whether these shapes support rewarded red or green. And I'm just going to not tell you about the task, other than it was really a test of whether the accumulation is in units of blood likelihood ratio. The monkey performed beautifully, this is showing he performed. He understands what the shapes mean. Let's listen to a neuron as the monkey is accumulating evidence. There's a response field, so the red or the green target will be here, the other target will be here. Okay, single trial now. We don't have to worry about whether these are averages of something else, but you can see that what was happening in the stimulus was we are providing more and more evidence for the red target, and there's this, which is in the response field, that mounting evidence is you can imagine, I think it's true, that you're seeing a gradual rise in the activity. Let's try another trial. The opposite pattern, first target favored the one in the response field, and then there was mounting evidence against it. That's what this is representing. This is the cumulative evidence for the green target now. That's what he chose, and there's a decrescendo in the firing rate. Here's a more interesting trial. Things sort of flipping around. There's an increase. Maybe you want to call this a step up, but if you do that, you better call this a step back down. Okay? Same kind of a thing. All right. So you're hearing on single trials neurons doing something kind of cool. They're doing addition and subtraction. They're doing it so happens in units of log likelihood ratio, which makes it even more interesting. But the important thing is, I haven't proven it to you. I'm just showing you. For all you know, it's reading tea leaves. The spikes are very noisy. So it's fair to be a skeptic about this. And so, but at the single trial level, it's pretty obvious, at least to us, that you're hearing neurons that are changing their state. They're not getting stuck in an up or a down state. Okay. And when we do the quantification on the averages now, we see this very nice relationship between firing rate in the brain and a kind of a unit of belief thing, but we've controlled the unit of belief by training the monkey to understand the symbolic meaning of each of those symbols. And more recently we've been doing things with reaction time, but we don't have time to get into that. I'll just play you a movie just so you get to hear these. No, I mean, I'm just all right, so you're seeing the same thing kind of going on. Now, I want to explain this graph to you because, I mean, we can be quantitative about this. We can look at trials where the monkey saw one positive shape and one negative shape, okay? And then on those trials, we can say, did the response change more than once? If the response changed only once, then all the firing rates of this would all be to the right, and not all to the right, things are noisy. And these should all be in the negative, because this is the negative going shape. But the idea is the responses in here are not expected if you're only allowed to step once. So that's just a way of quantifying the statement I just made with a few examples. Okay, so what might fail to detect diffusion in reaction time data? I'm already going to dismiss any failure to detect diffusion in a variable duration experiment where there's really no evidence that the monkey was integrating for more than 100 milliseconds. So the first thing to say is it's not easy, and so once again, the shout out that I think it's very cool what people are trying to do. People, especially like Jonathan, Manish Sahani's weighed in on this. Konrad's not weighing in on this. So I think it's a very good thing to do, and I want to support it, even if it's at times painful to me. Okay, so the animal. All right. So what I was saying. So one possibility in the reaction time data is that the animal wasn't integrating, or was using an extreme or snapshot model, or the integration times were short. Okay. Now the RT data that we're talking about here was data selected 16 cells from our set of 54 that I showed you, And so I'd like to think that those animals were integrating. I think we believe it. But to be honest, we only know it as well as those bits to reaction time and choice go. And so for all I know, maybe they weren't. But let's assume for a moment those animals really were integrating. So if the integration time is short, I just wanted to point out that we're really arguing about nothing because, as I said, it becomes scholasticism. You're arguing about how many angels are on a head of a pin. Because the difference between integration and stepping are really hard to get worried about. But another possibility is that the analysis was underpowered. So in the case of the right data set, for example, there aren't very many trials per condition, per neuron. We have many better data sets since that. Remember that Bregman was the first reaction time experiment in the monkey, and so choice reaction time experiment. And so we had half the trials were control experiments and so forth, and so and we've gotten better since then. So that's a possibility. I think it's a reasonable one. But the other one is another one is the failure to concentrate on neurons that exhibit ramp-like average firing rates. So if we look at the neurons that the 16 neurons, you'll see that there are some in here that they just don't look like they're ramping at all. So I don't know why we're trying to explain whether this is a ramp or diffusion or something. Okay. So now, it might surprise the non-experimentalists that we would have such neurons in our data set, but the fact of the matter is that when neurons enter, we have some entry criteria, and they come into the data set, and we don't throw them out just because they don't conform to our idea of what we want to find, right? So there's a lot of neurons. I'd say, roughly half of these neurons are, we would say these just aren't good examples to study. Now, they all contribute to those averages that I showed you, and it's not like there's nothing in those neurons, even the ones that are weak. Again, even this PSD, even the histograms here are underpowered. And then finally, Jonathan alluded to this already, so I won't really beat it to death, is that possibly a mischaracterization of diffusion, and really model comparison, as Konrad said, is only as good as the models that you're comparing. And so I won't belabor this one really. I'll just say that as Jonathan pointed out, I think he sounds like he more or less conceded, is that they didn't initially have any kind of stopping rule for the downgoing firing rates. And basically, through the machinations of the model, you could never predict late spikes. So what that meant is that if something should have had this downgoing rate, they couldn't really quite get it right because it would have predicted late spikes. And instead, it can never explain, it would predict zero spike rate late in time, and instead, the fusion really had no way of explaining these late spikes. So stepping could do it, diffusion couldn't, so there was the advantage. And even the validation of the model, if you just took their validation code and if you had negative, when you had negative going rates, these traces would be, they of course in the generative model that you're trying to validate, when you create spikes in diffusion, you would never create late spikes because the model couldn't do it. It allowed the rates to go to negative, the latent rates to go to negative, and then soft rectify to effectively zero. So you would never get late spikes. But of course, they're in data, and they could never explain it. So what Ariel did was add 10 spikes per second, like I showed you in the previous slide. And when you do that, then things that were created with diffusion are classified as stepping. So we thought that was an invalidation of the validation, of the model validation. And I'm going to skip the rest and go to the summary so we have some time for questions. So what I want to leave you with is that decision-making is these are very broad conclusions, is a model problem, I believe, at the nexus of cognitive psychology, experimental, and computational neuroscience. So happy to be part of this meeting, which celebrates those. Persistent activity is a substrate for computation. I hope I convinced you of that. It can step and hold, of course, but it can also represent graded quantities associated with evidence accumulation, belief, elapsed time. Those are the examples I showed you. And understanding the neural mechanisms of persistent activity is likely to bear on mechanisms of cognition and disorders thereof. And this third bullet point is what I think of as the heart of the matter of today, and those things called the soul of the brain. And so I appeal to you all. Let's get it right. Thank you.
All three speakers up here, and start off with Mike asking the question.
The speakers will go first. To the world. Maybe all three of you guys. So
You want a microphone? You want
Konrad, are you afraid?
So I'll ask you guys. We had 3 great talks with 3 very smart people that have their own ways of looking at this problem. But I would argue that the issue is we don't have enough information to cleanly decide or easily decide what model fits, right? Because we're trying to squeeze everything we can out of these spike trains. And I'm wondering, can it be solved with an intracellular recording? Because there you can imagine where now you have a continuous readout of membrane potential and simply ask, does this thing make a state shift up in a kind of up and down kind of way that would look like a step, or are things kind of ramping? And there are precedents for both of those dynamics that can be read out extremely trivially with intracellular recording. Is it that you guys want to argue, or should we just go in and get a pipette and do the experiment and see who wins?
I would answer that. Obviously, it'd be lovely to have intracellular recording. It'd also be, we'd probably be able to solve a lot of this multi-unit recording, although that's strictly the same. Intracellular recording is harder than it might seem, I think, because just consider the lesson from complex cells in B1. So they have up and down states, and yet the firing rate, will modulate in ways that are that don't really conform to what you might expect from intracellular recording. So you need both. You still want the spiking, I don't know. It can certainly help to have the information.
Jumping onto that, so why not just go the opposite direction? So simultaneous with your spikes, why not just record LFPs so that you get a sense of the global level of excitation or inhibition in that little tiny patch of cortex? Maybe that will give you insight.
That doesn't distinguish. The global, if you do anything with many neurons and average them, they will look like maybe the averages of steps, maybe the averages of fusions, and maybe even the averages of individual ramps, even though that wasn't on the table.
Fair point. I think what I was trying to get at, I think earlier, the first 2 speakers addressed this problem of unaccounted for noise. There are these things that are driving cells to fire faster or slower on certain trials. If you could access the LFPs, might it give you insight to that, unaccounted for noise? And once you can account for that noise, then maybe your model fitting doesn't suffer from some of the problems that it did before. I think that's the point I was trying to make.
I take issue with your question. So first of all, I don't agree that the statistical methods cannot answer the question. Whether we use cross-validation, marginal likelihood, DIC, WAIC, they give extremely consistent answers about which model was better supported. It's only the methodology that Konrad used that does not successfully distinguish these on simulated data, right? They all can work. You simulate data from one model that can correctly identify what model generated the data. I think the issue that Mike raised is more about, if we're finding stepping, is it because the animal was not performing integration? So that would be one sort of issue. The other issue would be we should consider alternate formulations of the ramping or stepping model that we haven't yet considered. So it's enlarging the family of models, and that gets to the issue of should we do more exploratory data analysis or find other ways to formulate new models. That being said, I do acknowledge that fitting to single trial data is not that interesting. And so I think either intracellular recordings or population activity, I guess I agree with Mike there. So we've done a little bit of analysis of paired recordings of pairs of neurons. And what we find with analyzing the stepping model is that the inferred steps are not correlated. So in fact, if it were a single step time that was being inherited by multiple neurons, you would expect that they would all step up together. And we found much better support for a model in which each neuron stepped independently. Now that would lead to an idea that perhaps, Mike, I actually don't know about these early analyses you described, that perhaps the average rate across the population would reflect the accumulated evidence, each neuron wouldn't. And I think that's still open. I think Mike doesn't accept that, and I'm not arguing that that's the case. I think we need to look at more data before we can.
But one small additional point is that there seems to be a problem that obviously the firing rate goes to 0 at a certain point, right? And that was one issue with an earlier model. You added spikes to kind of look at that. But an intracellular recording would, of course, allow you to continue to see what's going on there. So if you're pushing the thing down, the membrane potential should continue to kind of track down as well in a hyperpolarized way, where we're continuing to see information even though the spike rate is 0. It just doesn't matter.
Sure, these are just different models, right? We can have one model with a lower bound and one without a lower bound. We can ask which one is better.
Yep.
Right, but you're right that there's additional stuff we can see out of the intracellular data. When it's going to low rates, is it because of sub-threshold activity? I completely agree that, I haven't actually thought as much about how to use intracellular data to resolve this question as I have about population. So I'd love to hear your thoughts more about what we would look for specifically.
It's never going to happen, though. If no one can record from intracellularly from the awake monkey that I know of.
I'll do a stat overview.
But I want to clarify something here. So we know preciously little about mechanisms. So if we had intracellular data and we could show that the current or something is really sort of the log likelihood coming in or something, then would get us much closer to a mechanism. What we have at the moment is we have things that are compatible with that mechanism and a myriad of other mechanisms. For all that we know, LRP could be downstream of the areas where things actually happen, or it could be upstream, or it could be sideways, it could be wherever it is in there. So at some level, as neuroscientists, we want to ask the mechanism question. But what we can do as neuroscientists is typically not ask them and not answer them. And so the same thing is true here, and in no way is like this different from any other aspect of computational neuroscience. We have like little models, and they're very good models, and they're very appealing, but the actual evidence that this is how the brain does it is very unconvincing.
There are two basic features in the drift diffusion model. The one is the wrapping activity, and the other one is the bound.
We have discussed a lot about bound, but about the ramping activity, but we didn't mention anything about the bound. And the question is whether we have seen evidence that the bound can be manipulated, or if LIP represents a normalized activity, where should we search for such bound?
The phenomenon that bears on the question, we don't know the mechanism that's implemented, but what we know is this. If you change the speed accuracy instructions to the monkey, what happens is that the bound threshold on the firing rate stays roughly constant, but the starting point changes, and then the dynamic time-dependent, but not evidence-dependent signal, what I call urgency, that changes too. That signal changes. We think of it as a deterministic, but noisy, of course, not accumulated noisy, not Brownian, okay? Signal, that changes. When we go from 2 to 4 choice, and the animal's more invested in taking time because the error rate is now, 3 and 4, right? If you just guess. What we find is the same thing. Firing rate stays at the same level at termination. The signature of a termination on the firing rate is just that the firing rate has minimal variance at that point. Okay? About 80 milliseconds before the SICAP. But the starting point changes and the additive signal changes. So there's that level of control. Now, how that comes about, how you add a deterministic time-dependent signal to a stochastic, something representing the accumulation of random steps, effectively, we don't know. And we don't think the integration actually happens in LIP. I would say that much too. What we think is the representation of the integration is essential in LIP, we think, and areas like it. So it's part of, it's the place in the kind of place in the brain where it receives instructions, perhaps, of how to increment or decrement its firing rate from whatever state it's at right then.
It seems like from what Jonathan talked about and what Michael defined, there may be neurons that look different groups of neurons. Some that look like they're moving to intermediate levels of activity, others that just step up. And I'm wondering whether this is a property, inherent property of the neuron and its dynamics, or is it something about the behavior on individual trials? So I'm wondering, this is an experimental question, like I'm wondering if you could do an experiment where you do two kinds of tasks on the same neuron. One where there is an inherent accumulation of evidence requirement, and an alternative one where it's just a snapshot kind of experiment that Mike talked about. And you could look at whether dynamics were different in the two experiments.
We do that every day because that's the entry criterion for a neuron that's going to be sampled. It won't be true when we do multi-neuron recording because we won't be able to do it the same way. But right now with single neurons, or when we're still doing single neurons, we'll have a neuron that comes in because it was tested in a simple, what we call it overlap instructed eye movement, or memory-guided eye movement. That is a step. It's a nice example of that. And those same neurons, all the neurons that enter in have that property. Some of them still look great, and some of them don't look great. Some of them are better fit by stepping, I suppose, and some by diffusion. I do wonder about that.
Yeah, but isn't there an anticipatory buildup in that case when you're doing this just a card experiment? You have anticipatory buildup, so you can't really differentiate, or does that look like a
Now, I'm not even talking about the hazard rate experiment. I'm just saying the basic screening thing. Does a neuron have persistent activity? Is it spatially selective? If it's not, we can't study it to answer the question, will a neuron like that have diffusion-like properties?
But I think it deserves to be said that whenever we analyze large groups of neurons for, say, the time course of something, we find huge heterogeneity. Some neurons do it early, some do it late, some more like upwards ramping, some of them do some nonlinear things. Whenever we look for multiple variables, we find that kind of multiple of them are there. And you probably find that even if the ramping on average usually ends at the same firing rate or something, or the activity ends at the same firing rate, there will still probably be a representation of, say, how urgent we are in that situation. So all those variables are usually there, which makes it very hard to think about what we can learn about mechanisms.
That just makes some interesting questions.
So can you be a little more specific about that? So let's say we find that a lot of regressors significantly lower to the neurons. So they seem to be tuned for many different things. How do we get to a mechanism from it?
I mean, you don't get to a mechanism at all by doing correlations or system identification. You get to a mechanism by having a cool idea about how it might work and then designing an experiment to test it. You don't do, I'm too bad David's not here because she's a big proponent of this, but I think it's not a sin to have an idea about how something works and then design a cool experiment to test it. And, but I don't want to pick on Adrian because maybe she's changed the tune on this, I hope anyway, I don't think you can, the question of how the mechanism works is a question that first say, what are we trying to explain? And then we can decide at what level we want to even articulate our mechanism and design experiments to do it. I mean, what I love to teach students are the papers about what is the mechanism of building a complex cell. This is Tony Mocham's thesis in 1978. And that beautiful second paper of the simple cell complex and then some temporal dynamics, he was way ahead of his time. That was the hypothesis of how you build a complex cell. It was really a computationally stated hypothesis and a very cool design of an experiment that got at it. So I think that's what you do. You get to know the computation and then ask how you think it could possibly come about.
I'm happy to be a stand-in for Adrian. I would say there's also not a sin to take a regression approach and ask what's being represented. So I mean, I think that's the idea that all the neurons in one area represent one thing is unlikely to be true in the real brain. So I think a lot of studies have shown, as Konrad mentioned, that these neurons also represent other aspects of the task. Chris Harvey's lab has some, in rodents, has some recent work showing that information about trial history is also represented in the rodent homolog. So I think hopefully these two kinds of approaches reinforce each other when we build. There's a simple computational model, and we know actually the simple computational model of a complex cell can't actually predict very well, right? So it can't account for what a V1 cell does when you present a natural image. That doesn't mean that it's not a useful step toward, it still captures some core essence of what computation is being done. So I think hopefully these two kinds of approaches reinforce each other. The regression approaches identify other stuff that's not captured in the mechanistic model, and we can build better mechanistic models.
David Field tells me that the computational model doesn't even predict the simple cell.
That's great.
Yeah. Okay. So
I'm just going to register my objection with all that, just so you know. Because we won't have a discussion about it. I'm just going to register an objection.
To what David Field said.
Yeah.
You think it does? You know, what David Field has in his paper, what's the other 80% of the V1 doing, right? And that's where I get this stuff. So you dissent from that.
Yeah, I dissent from almost that entire world. So,
okay.
but I don't buy into the proof of extraterrestrial intelligence that you gave earlier.
But can I very briefly disagree with Jonathan here? So there's one way of thinking about it where we have these two kind of groups, and it's just like a sense of personal style. But there's another way where it gets to be an issue of substance, where we can argue how complex is the brain. And at some level, if the brain is really complicated, then we have no chance of just guessing the right model. And if we don't have a chance of guessing the right model, then basically trying a good hypothesis will not advance as much. If, on the other hand, the brain is simple in that way, then at some level the best thing we can do is guess and try and falsify. And where we are on that continuum, we don't know. But like at some level, this isn't just like a matter of style. It's something that we can potentially answer.
I mean, just to give an example, someone has a hypothesis that the reason you can have persistent activity is with recurrence, and that persistent activity could look integration-like because that same recurrence is competitive with other things that are, okay, that's a very popular model. I associate with Shadlen, but many people have worked on it. Okay, so you have this idea, that is kind of a mechanistic model. I mean, it's not stating neural cell types, it's not stating the exact connectivity, but it's mechanistic sounding. So you test it. You can say, well, then it ought to be sensitive to a gap between two samples of evidence. Let's vary the gap and see whether that affects performance in monkeys and humans. And it doesn't. So you say, okay, end of that. That one problem with powerful models is no one ever wants to give up on them.
So this is interesting because I could ask a million questions here, but I'll try to just ask one. So you're all throwing around the word mechanism, and I agree with what Konrad said earlier that basically the models stand in for mechanism. And you can't ever prove anything in natural science. You're just going to say this is the current best mechanistic model. At least that's my view. I don't know. Maybe you could discuss that. But you're also both talking about, from LIP, encoding what I call encoding models, which is essentially the focus of this whole debate. Like essentially what's the underlying driver of the LIP, which is in the class of encoding models. Although the reason these studies are even here is that Biddle and Mike and others showed that it's the link to behavior of these neurons that was so interesting. And then, so that's really, when you say the word representation, you all sort of said that. When I hear you say that, I hear you sort of making a statement about the belief of the neurons to some behavior. Do you even agree what that word means? Because you're not using it in that common language. And I don't, maybe there isn't a well-informed question here, but I think you can't just throw that word around without a definition. And really what we're after, and Mike sort of said this on his talk, hey, those rodent people are doing population decoding. I don't believe them because they're not predicting reaction time. You sort of threw that in on one of the slides. And we can make equal arguments about the work that you guys have done on LIP in predicting behavior. There's always some limit as to what you're going to predict. So can you guys even agree on what LIP does in terms of the animal's behavior? Is that even something you guys want to agree on or state anything on? Maybe Mike will at least. What's the model between the neurons and the behavior that you believe? What does representation mean to you? Just to try that.
Representation is just a general word for, I mean, not using it in the mathematical sense, or the philosophical sense. I mean, in the very colloquial sense, that there's a quantity, a firing rate of a neuron, or a latent firing rate that we could get over for many trials on the assumption that if there were many neurons like it, we could get that firing rate on one trial, it's a ergodic assumption of a neurophysiologist. And it conforms to the changes within some very simple transformation, like scaling. It conforms to a quantity that we think mediates the behavior or is of relevance. We could be talking about something very passive, like the color or the intensity of light or something, or motion energy in the sensory side. But I would use the word representation very loosely like that. Tying things to behavior, I think, is important. Tying things in your interpretation of what the firing rate means, tying it to what I don't know who coined the term projective field, but as a cousin to a receptive field. But thinking of where those neurons project, who's going to hear these spikes? Well, the frontal eye field and superior colliculus for sure are going to hear the spikes from LIP. So I'm going to think about LIP in terms of knowledge of space as a possible place I might grasp with the gaze. That's Helmholtz uses those terms. And so that's a way to think about knowledge, period. So for me, representation is not about things, it's about knowledge of things, is about what you might do with those things. And so we've got into a real discussion about representation. I would say that representation is overblown in neuroscience. But
I want to try to give a very different answer. So representation for me is just the best predictive model that I could have for something. But the important thing for me is mechanism. And mechanism for me is defined in terms of causality, and I take the standard potential outcomes framework that people use to define causality, which is if I took something in the brain that could be a neuron, it could be a brain area, then the causal effect is defined as what would happen if I would interfere with it, which would be if I would stimulate it. And for a neuron, you could say, I am interested in its causal effect, in the way at least I think about the brain, which is I want a model that predicts what would happen if I would stimulate. And as a field, in most situations, we aren't there yet, but both electrical stimulation, there's been beautiful experiments on biasing with electrical stimulation, and optogenetics at least open up that path. And whereas the representation of all this, just like the fit that we do to the data, it doesn't mean anything. At least not for the way that I think about the brain. It has no mechanistic connotation for me.
Yeah, I can agree with that. I think of representation in terms of prediction. What variables would allow me to predict the spikes better? So I tell you the trial history, if I tell you that the last trial was a rightward trial, and that allows me to predict the spikes better on the next trial, then that's something that's being represented. Or similar, that could decode the previous trial from the spike rate on that activity. But that's not a mechanistic claim. I think actually in LIP we have competing evidence about causality. One is the microstimulation experiments that show that microstimulation in LIP can bias behaviors, and then Alex Huck's lab has also done silencing and shown that the animal can perform the task at the same level while inactivating LIP. So those seem
different tasks. Be careful.
On a different task, yes. So I think the jury's still out as to where, what is LIP's causal role? What mechanistic role does it play? Whether it's efferent's copy or whether it's...
But let's suppose those two results stand up, and you have, we're working on this now too, small experiments in LIP. Let's imagine it was the case that the stimulation of LIP shortens the reaction time when you make that choice, and also increases the probability of making that choice. The weak effects, they have a nice quadratic relation that's predicted, they conform to the diffusion kind of framework, so that's kind of nice. Okay, you have that, and let's also suppose that you inactivate LIP and you get no effect. Okay? Now what does it mean for you? You have to think about what you mean, Konrad, especially about causality. Here we have, I showed you neurons in MIP and LIP doing the same thing, and if we went to the speech system in a human and all kinds of ways that we deal with leftward and rightward, what we have, I think, in the brain is a parallel, intentional, not representational, but intentional architecture for dealing with information. Okay? And so that means that once we get out of the things near the sensory system, where if you put a hole in it, you better not sense, say, sweet or bitter or something like that, or near the motor system, where if you put a hole close enough to the apparatus, you better not be able to move the syrinx or something, But you get, and this kind of is part of your chaotic, whatever it was called that you did, like long. The idea that, distributed systems, or in this case, relatively simple parallel kind of processing of information because it supports different kinds of things we do with our bodies, okay, is just a really easy way for me to say, well, of course, you don't really need that, assuming you have a mechanism to cultivate another pathway. I think this is an area to be studied in the future.
If I could jump in very briefly, that I think as someone who's been in this for a very long time, the removal experiment is the thing that always drives you crazy in neuroscience, because I don't know a single mechanism of the kind you just talked about, for which we have lots of positive evidence that this is clearly causing X, but we remove it and we can still get X. And I'll give you a spectacular example of that from something I work on at the moment. So there's huge evidence that the cerebellum, for example, is causally involved in mediating the conditioned eye blink and timing. And so very excited about that. But there are a few patients out there in the neurological literature who have a congenital absence of the cerebellum, right? And apparently they get along reasonably well. But now here's a fact. Something like 80 or 90% of all the neurons in the brain are in the cerebellum. So I don't think we want to conclude that all of those are just there for decoration, right? So I don't know how to explain the fact that a patient can get along fine without, but the same thing's true for all of these. You anesthetize and the motion center, and at first it has an effect, but then it goes away, and that's always true.
There are a few other things to throw in for the group here, if you haven't thought about it, is that all of the really interesting, successful experiments with microstimulation and the visual system are always done near threshold, when people are doing threshold psychophysics. And if you look at the ends of those psychometric functions, where things are, say, easy to the right or easy to the left, there's no effective stimulation. And if Bill Newsom and Dan Salzman and Ken Britton, that first paper, had they only done easy conditions, they would have concluded MT clearly not in the causal chain for this. Okay, that would have been their conclusion. And I would like to always ask people, you know, what studies do you look at when you're doing your NMDA blockade or whatever the fancy dancy thing is now, express, you know, channel adapts and all the inhibitory neurons, and you find that you don't get an effect. Well, was this like a high threshold? I mean, a super threshold when you had to swim for your life in the maze, in the water maze, or is this close to low signal to noise? And I don't know, maybe you can say, well, close to low signal noise. What are you getting at here? You're getting at very weak effects. They're not obviously they're not going to violate the conditions for necessity.
But I mean, that's something we need to keep in mind. The effect of any individual neuron, the causal effect of anything that's downstream, should always be extreme. We have a pretty large number of neurons in our brain, and why would any one of them be like all that important? And the difficulty of this whole region effect is that, well, they are all different neurons, and downstream someone's trying to interpret that all those neurons jointly went quiet. And that is very different to saying what would happen if we had individual perturbations. And we don't have techniques at the moment with which we can reliably choose, well, these 100 neurons, I want to like stimulate them in exactly the right way to produce this pattern.
Yeah.
I want to disagree with all of you. Let me start.
Here.
So let me start first with the comment about a congenital problem. So independent of the number of neurons, if you've now learned to adapt to that condition, and you've had a plastic nervous system, developing nervous system, you're in a position now to use different circuitry to solve the same problem. You're probably not solving it as well. And the answer to how that person does reasonably well is that he's a person. And he's doing reasonably well in a supportive human society. That's the answer. And a similar problem is relevant to all the comments you were making about manipulating the brain. If you want to really study the problem, put the animal out in the natural world and see how well the animal does. The things we do in the laboratory and the ways we measure behavior, which are pretty weak, are not the same challenges that animals have either surviving, tracking a mate, finding food, and so on and so forth. So I think you have to be very, very cautious about drawing conclusions with sort of weak and not thoroughly examined behavioral analyses and drawing conclusions about the adaptive significance of some circuitry or the loss of some parallel pathway, one of a parallel pathway that contributes to the whole animal's actual behavior in the world.
But you promised to disagree with all of us. I don't think you said a single sentence that I wouldn't wholeheartedly agree with.
Okay. I didn't hear you saying that.
But you said several, and I would. Yes, Dave.
Hi, this isn't really my field, but I would like to, and maybe this question has already been asked and answered, but it has to do with the notion of what is decision-making and or the locus thereof. In other words, we now have, the subtopic was accumulation of evidence and decision-making or something like that. So in some ways, this the very impressive way that the firing comes together 80 milliseconds before the saccade, independent of how long it takes to get there, and independent of the difficulty of the problem, is very, very convincing for this being an expression or an index of, at that moment of the decision to do this or that. But prior to that, you had said, I think, Mike, that maybe it's just indexing something that came from somewhere else. And yet, the possible heterogeneity of these spike trains, some of which may be stepping up and down, which seem to reflect some input that's being calculated there, it would appear, or at least that's where the accumulator is accumulating in that neuron at that moment. You put on one more little funny shape and it goes and take away. And that was a very impressive experiment. It seems to me that, let's say, taking Michael Wohn's story of the synaptic organization, where a certain kind of promiscuous connectivity between the cells cells that have very different timing with respect to something or other, can converge to create, if you will, what might be superthreshold or perhaps step-like changes in the recipient of the convergence that results in a very, very precisely timed burst related to singing. So that kind of image of the internal circuitry, it seems to me, could be a model of decision-making process based on uncertain neurons and their ultimate convergence. And is this way of thinking that make any sense to
me?
To anybody?
I definitely. I mean, some of the things you said I resonate with completely. And when I hear, these beautiful timing studies in the bird, I think of, I usually think in terms of motor sequencing. But even if you want to be flexible with time, it's not the case. You set yourself in a mode, and you turn on the go switch, and 500 milliseconds later, something hits a threshold, and you're destined to go. It's more like you're doing things flexibly, and then something organizes your behavior, another computation presumably, perhaps dealing with costs of time. I'd like to think that it also might involve some kind of dynamic that might even look diffusion-like. It doesn't have to. But whatever it is, it could presumably control, no more processing now, control the way another circuit will finally produce that burst to get out. And so that's the way it's more of a manhandling, person handling, the way that we organize behavior, given the cost of being flexible with time.
I think it's also interesting to think about learning. I mean, like, we have that circuit, we observe it after learning. Learning can allow a system to solve a problem in an arbitrary number of ways. And if learning in brains is at all the way learning is in machine learning, it will generally come up with good solutions for that class of problems. So in that sense, it's possible that because the bird's brain solves a certain class of problems, it comes up with one type of neurons, and it's possible that for, say, LIP-type decision-making in the real world, that it would come up with a huge heterogeneity of different responses that just allow solving for natural situations the problem in an efficient way. And it's possible that we as humans can't understand it anymore.
I don't want to end on that pessimistic note, but I think this was excellent, exactly the kind of discussion we hope to have. I thank all of our speakers, and I thank the audience.